Okay, folks, hello and welcome to our exclusive by invitation only pre-launch event. We're delighted to have so many of you in the room with us and online to be among the first to hear about what we've got coming out to the market before the end of this very month. I'm delighted too to be broadcasting from the heart of the physics building here at Queen's University in Belfast. This building is a very important place in the history and the journey of Andor Technology, now an Oxford Instruments company. In fact, this is precisely where our journey began back in 1989. And as such, I have great pleasure in inviting one of our founders and today our technical director, Dr. Donal Denver, to the podium now. So if you could please give Donal a warm word of welcome.
Thanks, Johnny. Right, I've got some notes, but I'm not sure I can read them without my glasses, so I'm not sure how useful they're going to be. Oh, technical difficulties. Right. Johnny has prepared some slides, and he actually understands better than he thinks. This is the little journey he wants me to talk, and I've got a few signposts to guide me. First one is roots. But actually, very smartly, he's actually made it kind of winding, and that's a good demonstration of, that in fact, most of the time we didn't know what we were doing or where we were going. And that's just what it's like if you start a business. In fact, it's not knowing what you're doing is almost essential. If you understood what you were getting into, you mightn't start. He's also put in little gaps. I think that's meant to represent the various potholes that happen as you go along. Because there always are some. So I'm actually going to go back one. And we're not going to talk about the potholes. This is going to be the sanitized version of a short history of Andor. I will doubtless leave lots of things out, but so be it. The company actually started in a room in the basement, almost directly below here. We may have moved across the corridor at one point. That's not a complaint. In fact, the goodwill of the people in the department was essential. Without that, I don't think our little enterprise would have got off the starting blocks. And it was 1989 was the year that we formed the company. But actually, back in the middle of the 80s, I was building equipment and we were part of a research group doing spectroscopy, laser spectroscopy. We built equipment and we thought about starting a company, but it kind of didn't go anywhere. I just don't think we were ready. It was actually only in '89 when there was maybe a better group of people who understood better about starting a business. In fact, we didn't understand anything about it, but we did anyway. And there were a couple of people I got to mention, which is Hugh Cormick and Mike Pringle, who were instrumental in getting things going. And also a guy, Eugene Arthurs, who was then president of Oriel Corporation, because that allowed us to sell our product. And the product itself was born out of, we were a group of researchers. So we use a lot of equipment from different places. And one of the frustrations that we always have is it never quite does what you want, or maybe not the way you want. And it eats up a lot of time. And so we thought what we want to do is it wasn't necessarily inventing a whole new piece of kit. It was really about, can we not make this in a way that is actually easier for a researcher to use, doing the things that you as a researcher want to do. Now, the equipment at the time was actually image-intensified diode arrays and CCDs, which were computer-controlled and connected to spectrographs. So they were sensitive imaging equipment. But we looked at it and we thought, right, you've got to sort of get the computer and the data acquisition and the displaying has to go a lot quicker. It's got to be instantaneous. If you're working in a lab and you're setting stuff up, you need to feel that when you do something, you see the effect. Instead of waiting and wrestling with bits of gear and synchronizing it to other things, trying to choreograph it with other equipment, it can consume an awful lot of your time. So what our angle was, we want to make something that is really easy to use, does what you want to do, and does it the way that you work. And that was our first set of equipment. We sold that through Oriel Corporation. Again, most of the customers that we would be dealing with would have been, it was all about very sensitive detection. So one of the things was that the detectors, which were then moving away from image-intensified data arrays to actually CCDs, they were becoming sensitive enough, but they needed a lot of cooling. Now, cooling would, if you want to cool something in a physics lab, you just sort of go to the corner and get the jar of liquid nitrogen out and start pouring it over stuff almost. It's always there, it's ubiquitous, and we used to splash the stuff around. Health and safety wasn't maybe quite as strict as it is today. But it's a very clumsy way to go about doing things. And it's, again, you're supposed to be doing research. You're not want to have your time eaten up wrestling with equipment. And of course, around you, the idea of vacuums and the TE coolers and things, they were, we were aware of them. Sort of thought, this has got to form a better solution. Surely we can make, a hermetically sealed chamber to put the detector in and cool it with a TE cooler. The vacuum is essential if you're really going to try and get very low temperatures efficiently. And you want to make something that didn't need any maintenance. You come in the morning and you just use it and you forget you're using the equipment, so you concentrate on the work that you're actually being paid to do, which is not to wrestle around with trying to get one piece of equipment to work with another piece of equipment. Now, it didn't turn out to be so easy to make that permanent vacuum chamber. However, you sort of kept thinking, well, take a light bulb. A light bulb is a permanent vacuum, and you buy them for pennies in the shop. So it's not like it shouldn't have been hard, but in fact, there is a lot that goes into doing that. We saw, right, we need to find a way to produce that, because that takes another burden of wasted time away from the researcher. That was the second part of our growth. Also regularly pumping down the vacuums. This had to be permanent, and you buy it, you use it, you think of it as a piece of electrical equipment. And I'm one slide further on, Johnny, sorry about that. Now, at the same time, this was actually in the 90s, and there were a couple of companies, EEV, as it was then, Marconi, and Texas Instruments in Japan, had actually been working on CCDs with inbuilt electron amplification. And we could see that these would be the next wave would replace the CCDs that we were then using. Whenever we took these and we said, right, okay, this is the right thing to get into the imaging market with. So we started to build them in. We were also trying to think, now they had different names for them. Whenever we made the first product, they were actually into the market that we were then in, which is not primarily imaging. It was actually spectroscopy. And so the first products that we shipped in the late 90s were actually going on the back of spectrographs. These were EMCCDs. And before that launch, I think it was only days before we launched them, we had to decide what name would we give to this stuff, because this was the first of these going into the market. Some had been sold into some defense applications, but that was it. So we thought about different names. They had Impactron and L3 Vision, and we sort of thought we need something that's nice and simple. That's where the EM came from, just electron multiplying CCDs. People were familiar with CCDs by this stage, so all we wanted to do was hang right on the back of that. And so this is like your CCD, but it's a whole lot better, which it was. So, and in fact, EMCCDs today are still some of the most sensitive detectors that you can buy. That name, which we coined literally, I think, a week or so before we launched the first product, then became the de facto standard, and everybody started to use that as the term to describe EMCCDs since, including even the manufacturers of the devices. Even during the EMCCD's early days and heydays, and was growing rapidly, we could see that sCMOS was becoming a more important or a bigger technology in the imaging market. Back then, that would have been even in the 90s and early 2000s, you could buy sCMOS sensors. They were pretty rubbish, by quality standards, but they were beginning to get used as webcam type things and little cameras. The cell phone industry was starting to get interested. Digital stills cameras, actually, and the cell phone cameras were originally all made from CCDs, but they were moving into CMOS. And we could see that this was somewhere or another was going to play some part in the next wave of detectors. In science, the things that we are interested in are the very high quantum efficiencies, very low noise, and they definitely didn't have either of these things in those days, but there wasn't anything fundamental to say that it couldn't do. Now, that wasn't going to change by the requirements of our industry, that is the research industry, the science industry. The industry that really got the money pouring in to do the necessary development for CMOS was actually digital stills cameras and cell phones. I mean, these were multi-billion-dollar consumer markets, and therefore research money would find its way to improve the processes which underlie CMOS. And we could see that somewhere in here, some point, this was going to get good enough that it starts to play a part in scientific imaging. Now, seeing that, I mean, I'm sure we weren't the only people that could see that, but seeing it and actually bringing the different bits together is a different matter. It kicked around, we talked to people at different times, but it was really only around 2006, I think it was 2006, we actually got the right group of people and companies, like-minded people, to sort of go, right, we think that with the processes that are available in 2006 at some of the fabs that make the digital image sensors that are used in cell phones, they could make something, we could design something with their design rules, being tied to their design rules, such that it would be good enough for scientific applications. We weren't looking to better EMCCDs or not. It was really just, is it good enough to play a part? And our feeling was that it could do. The noise needed to be got down. The QE was probably all right. But the desire for it was that we were also seeing at that time in the EMCCD market, people loved them because they had the sensitivity that they needed, particularly for fluorescent imaging and a bunch of other stuff. But where they start to peter out is whenever you want more pixels, multi-million pixels, and you want higher frame rates, the CCD technology just starts to run into a brick wall. But CMOS, with its massive parallelism, multiple readouts, is easy. And therefore, it had that solution. If we could only fix the readout noise, the QE would do, and that would make a good product that would find a place in the market. Key to this was a company, Fairchild Imaging, and particularly one of the engineers there, a guy called Boyd Fowler, and he was their chief engineer in the group that he had. And a conversation somewhere started, and he felt that this was possible to get the kind of sense that we wanted. That was a sensor that was big enough, had enough pixels, had the right size, could get low noise, could have the QE, and fill the quality area of an imaging microscope. That was the remit. Now, you know, it took a few years in the design and getting the bugs out of that, but the result was everything that we had hoped it would be. And those sensors, the first two sensors that came out of that development was actually the 5.2 megapixel and the 4 megapixel rolling shutter only device, which we sell under Neos and Xylas. That was the product of that, and it did everything that we wanted. In fact, we got sub-1 electron noise, which was way more. We really didn't think we were going to get there. And that was launched, I can't even remember now, but it's somewhere in the history. But it's, you could see the thing we wanted to fix next was actually the QE. In fact, we did back illuminate a couple of those sensors back in 2008 or 9 somewhere. But we couldn't get a commercial way of doing it. The sensors didn't work, they worked, but they didn't work well enough. And part of the problem is there's a little bit of something maybe worth understanding. In the CCD world, the fab plants where the CCDs are built, they're big, they're tens of millions of pounds worth of investment, but we are big customers to them. The science community drives quite a lot of them, particularly astronomy and stuff. So they listen to what we want. And they develop processes like the back illumination and low noise amplifiers. And if they work on those things because we want them, they're responding to us through to you, the customer, who's actually doing research in the labs. CMOS is a very different world. A CMOS fab plant is tens of billions of dollars of investment. They are driven entirely by digital stills cameras, cell phones, and now increasingly automotive and a whole host of other consumer-type applications, from mouse controls and all sorts of stuff. So you can understand that they really don't respond to what the science community, even as an entire community, goes. So we're always trying to find some way to use what they're developing to get what we need to do science. And that road still has a bit to run. I said about the back illumination on purpose because we could see that there was no technical reason that we couldn't get better back illumination on CMOS. That it was completely compatible, but it just wasn't happening. The noise, getting the noise floor down, that is also possible, but it's not going to happen as quickly is what I think. We have to go with what developments are being pushed mainly by those consumer markets. Now, consumer markets actually think back illumination sounds exotic. It's sort of only for the science guys, for the astronomers who fuss about everything and want infrared and UV and everything all at once. But in fact, those consumer markets are interested in back illumination, and they were developing processes. They weren't necessarily exactly what we wanted, but they were getting close enough. And this is really where the latest CMOS, which Claire and Colin are going to talk a bit more about, that's where they have come from. The processes that were developed in those fab plants were good enough, or we could be adapted enough to actually produce a back illuminated CMOS version of the sensors we were making. And now we're getting there. I wouldn't say the QEs are exactly as good, but they're pretty damn good. We're up at 95%. We'd like more infrared, we'd like more UV, and all of that will come in due course. Don't ask for a date. I don't. The noise, I think, could be a little slower, but lots of more good things are going to come. Is there anything else I wanted to say about that? Last slide, I think. Sorry. I think I mentioned about the fab plants. The reason I think that there's probably going to be more developments in CMOS is that, okay, that industry has been going for quite a while, and yes, the consumer markets are there, but it has left behind, if you like, a lot of infrastructure in terms of fab plants and stuff who have things that were really interesting to us, and hence to you. And that's, these fab plants are necessarily, you can sort of say, I don't want to say they're out of date, they're not really, but they are actually taking more interest in science, and they're beginning to listen to what we, as a company and as collectively as a community, the research community, want, and they're beginning to respond to those, which is why I think that we will see more improvements as we head down this road. I think I've said enough. So I would like to pass over to our head of engineering, Claire Greenwood. And so if you give her a little hand. Thanks, Claire.
Thank you, Donal. I only have a short bit to say about product development, specifically about this new product. Through all our product development that we do in Andor and Oxford Instruments, we try to keep you, the customer, at the centre of every single thing that we do. From the features that we're providing to the connectors that we use on the back of the cameras and on all of the other products. This specific product has been designed with the academic research market in mind, and you'll see that whenever Colin talks in more detail about the features that we have developed for this product. We do this through deep, genuine understanding of what you want as our customer and the research that you're carrying out. But this product development, what we've tried to do is go back to basics, and we've designed the camera from scratch. This meant that our design team was allowed a bit more freedom in our architectural designs, and we're able to support lots and lots of different features based on what you, the customer, have wanted from us as Andor. This allows us to give you a lot more flexibility in the different types of features we have, but also to ensure longevity of the product when it comes to market. What we've really tried to do is put real energy and focus into the full customer experience, not just about those features that we're going to talk about, but also about when you receive the box. When you receive the box from shipping, unboxing it, setting it up and using it in the software, and making sure that that is taking all that time away, that you're not spending all your time trying to work out how to set the product up. You're actually using your time to do your research, and it's easy to use, and it gives you a better customer experience. So the future is still a journey. This is just a picture of my daughter, actually. But wanted to bring the point to what the future is. Well, actually, this product is the future. This platform has been built from scratch, and it has been developed to allow really rapid integration of features that we have developed along with our customers. We've provided rapid integration of new features, rapid integration of the camera into third-party software. We're providing different interfaces and cooling methods that are aligned with the type of research that you'll be carrying out. So what next? So again, it comes back to the customer about what you want to do. We want to encourage really open conversations about what you're doing today, about your needs. We've already provided some support for specific applications. So for example, in physical science, we've got low latency modes for adaptive optics, wavefront sensing, we've got lots of spectroscopy features. And in our life science, the roadmap includes surf, stream, super resolution features that we're developing in partnership with Ricardo Enriquez from ULC. So this flexible architecture will allow us to integrate those new features that come from the scientific community easier and quicker. So my part was really quick, you'll be glad to hear, but I'm going to hand over to Colin Coates, who is our product manager for research, and he'll introduce to you the first cameras coming out of this platform development.
So hello everybody. Okay, so Claire mentioned we've developed a new platform from scratch. So arising from that, we're going to launch actually 2 new camera families. The first one on the left-hand side here is called Sona, and it's really the life science platform from this platform. Or sorry, it's the life science product family from this new platform. And it's actually the first that will launch. It's going to launch next Tuesday, the 24th, just to give you a date. And it's been designed and featured primarily for life science applications, and in particular, really for fluorescence microscopy applications for that whole general field. So, typical usages which might benefit from the Sona would be, developmental biology, imaging of developing embryos, high content screening, neuroscience, imaging of organoids, things like that. So we'll talk a little bit more in detail about that later. The one on the right-hand side is called Marana, and it's a physical science-oriented camera. Again, it's been designed and featured primarily for physical science and astronomy applications. So applications that might benefit from this camera, within even astronomy, you could think about this whole area of fast astronomy. Each of these cameras at launch will be based around the same sensor. And it's a 4.2 megapixel sensor with 11 micron pixels, so a 32 millimeter diagonal. So quite a large sensor, and it'll be fast as well and low noise. So for the likes of astronomy, this camera will be really, really good for the general area of fast astronomy applications, things like space debris tracking, near-Earth object detection, scary asteroids that are coming far too close to the Earth, things like that. Solar imaging needs fast and sensitive cameras as well with larger fields of view. There's a general area of astronomy called high-time resolution astronomy that just studies fast stuff that happens in space like pulsars. So that's the 2 platforms. Now, there's some common technology inclusions that we've built into both camera families, sort of cross-platform. And I'll mention a few of them here that will then serve basically well for various types of applications. One of them is the fact that we've introduced, as Donald said already, we are experts in vacuum cooling, thanks to Donald's early efforts. That's carried across very much into our sCMOS technology. Not a trivial thing to do, it should be said. CMOS has a massive amount of parallel outputs. That is a hell of a thing to overcome to then create a vacuum solution for sCMOS technology, but we've done it. It took a while, but we've done it. So these cameras are vacuum cooled to -45 degrees. So in there basically is a core sensitivity statement. So these are back illuminated cameras. They have high quantum efficiency. They're really efficient at catching incoming photons. Okay, but that's only one of the parameters of sensitivity. The other one, which is far too often overlooked, is the noise floor of the sensor itself. And that's what we really have to try and minimize to be truly sensitive. So the analogy I like is just to think of an object sitting in grass. So quantum efficiency will catch more photons and make the object bigger and make it more detectable. But there's a lot to be said also for going and getting a lawnmower and cutting the grass and making the object detectable that way as well. A truly sensitive camera does both. So you can't really have one and not also do the other, or else you'd be compromising. So that's what vacuum cooling to deep cool temperatures contributes to. It helps cut that noise floor right down, helps cut the grass. This is our lawnmower. So with that comes a key claim. If you've got the highest available sensitivity and then the lowest possible noise from these sensors, then we simply have the most sensitive back illuminated sCMOS available. So that has loads of application benefits, which we'll talk about later on. But our general position here would be to say simply that if you're enamored by back illumination is very popular. It's very sought after for a reason. The reason being enhanced sensitivity. So the core message being, if you're going to pay the extra money for back illumination because they are more expensive detectors, then you may as well make sure you're considering the most sensitive implementation of this high-end technology, and that's the key message. So aligned with Donald's earlier comments about vacuum technology, it doesn't just stop. The benefits don't just stop at deep cooling and low noise. There's actually a really important aspect around protection of the sensor and longevity and lifetime of the product and avoiding the need to return it back to the factory for repumping, things like that. The alternative to vacuum technology, which is still used by the majority of providers in the life science space especially, is called backfilling. It's basically where you're using a positive pressure of dry gas in the sensor enclosure, and it's sealed really only by O-rings. So of course over time there's going to be exchange with the atmosphere. O-rings are not hermetic seals. The dry gas backfill itself is only dry to a certain extent. So that means there's moisture in there. That means there's organic, there's volatile hydrocarbons and organic things which will attack the silicon over time. It will take time to attack it, but it will attack it over time. And it will create performance compromises, not just in the cooling eventually failing, but actually it will attack the quantum efficiency of the detector over time. So its vacuum sensor really, really provides a very sterile, protected environment for the sensor. So if you're really thinking about longevity, it's a very, very strong consideration we all should be making. So yeah, that's the protection of the sensor is one thing, but the moisture is another thing. Over time, you don't want moisture building up in the sensor enclosure and actually appearing on the sensor itself, or appearing even in vacuum systems on the outside of the window. There's convection currents in systems which have gas in them. So if you've got a cold sensor, convection currents, you're going to cool the window. You can, in humid environments, get moisture on the outside. So these are all really relevant things that are then overcome by vacuum technology. There's one more core technology which spans this particular first release I wanted to mention. So as it happens, this first back illuminated sensor, which has been commercialized, back illuminated, sCMOS sensor, which has been commercialized and brought to the community, actually has quite a serious problem with it. It glows. It glows around the edges of the sensor. Now, that's for a low light detector quite a bad thing. These are ultra low light cameras. You don't want to have the sensor itself as a source of photons, and therefore layered on top of your low light signal. So what do people do about this so far? A few different attempts. You either just live with the fact you've got photons on top of your low light signal, or others have only read out pixels from the middle part of the sensor. They just said to the sensor, pretend you're smaller than you actually are. You're not really 4 megapixels, you're only 2 megapixels or smaller. And therefore, they didn't have to read out these areas where there's light generated by the sensor. Or others have said, okay, well, we can't allow this, so this becomes noticeable over time, so let's limit our max exposure time to 30 milliseconds. So of course, that's very, very limiting. So Andor are the first company to have properly tackled this problem and said, now, well, let's do something about it. Let's introduce a technology to suppress this effect, massively suppress this effect. Therefore, we can use these pixels again in a quantitative sense, and they're not going to contribute to the signal by themselves. So that's what we've done. We've introduced what we've called this anti-glow technology. I'm showing the bottom half of the sensor here with the anti-glow off and the anti-glow on. You can see it makes quite a stark difference. So what that, from an application perspective, enables us to do is access the full sensor. So I said it's a big sensor. We can now access the full field of view. So for applications within life and physical sciences, that's really, really useful. So I've talked about some core technologies to both platforms. For the rest of this section, I'm going to try and focus it down into the camera, which we're launching first, which is the Sona for life sciences. But before I do that, I'm going to play a first, like a 1.5 minute video, which we've put together, just that touches on some of the main points of this camera and its relevance to microscopy. So I'll play this first. Okay, so the video itself touched on a few good points. I'll go through a few in a little bit more detail here, but before I do that, I should mention I've written this technical note, which I think is going to be quite useful for people. Simply saying if you're in the market for purchasing a back-illuminated sCMOS for microscopy, then we've grouped together some of the technical explanations as to why we think Andor is a damn good choice and should be strongly considered along that process. So I would encourage you, once we do formally launch, to seek out this technical note from our website and have a read of it, because it'll go into much more detail on some of the stuff that I'm about to mention. So let's revisit the sensitivity claim in the context of microscopy. So what we're doing here, we're actually seeing the QE curve versus what is the current highest QE curve in terms of front illuminated sCMOS technology. So it's not to disparage it, it's actually for front illuminated a very, very QE curve, very, very strong, 82% max. But the true reason people are enamored by back illumination is this is a nice visual curve, and this is the best of the best, gets you right up to 95%. That's what back illumination brings you. So as I mentioned, we're combining that with our very, very unique method of cooling, and that lets us drive down our cooling temperatures and therefore drive down that noise floor to the lowest possible level. So that's really what we're doing. In the context of fluorescence microscopy, then there's lots of application benefits that you can associate with the sensitivity that these parameters bring. For example, we're talking largely about fluorescence microscopy. You have to put laser light in to cause a fluorescent dye to emit photons. But excitation powers are generally an undesirable thing in microscopy. So by reducing the excitation power, by reducing the flux of impacting photons, you are causing less damage on the cells, reducing the phototoxicity, therefore keeping your cells and tissues, your living cells and tissues alive throughout the course of the study, which is a good thing. But of course, with lower excitation powers comes lower signal levels, so you have to counteract that somehow, and that's where sensitivity comes into it. On a similar vein, you can lower the concentrations of fluorophores and dyes that you load into your cells. There's like an observer effect in fluorescence microscopy. The act of observing something perturbs what you're trying to see in the first place. That effect is alive and well in fluorescence microscopy also. You affect the physiology of the processes that you're trying to see by loading too much fluorescence dye in there. So again, reducing the dye reduces the signal. You counteract that with sensitivity. It could be, simply following faster processes means you're going to use shorter exposure times. So again, shorter exposure times, lower signal, we need higher sensitivity. In fluorescence microscopy, we often use modalities whose very nature are to exclude photons. Modalities which are there to kick away the photons that are slightly outside of the focal plane, and only accept photons from a very, very thin sliver of excitation from within the focal planes. Modalities like turf and spinning disk confocal being prime examples. So again, they're inherently low light, and they're really, really well suited to sensitive detectors. So I mentioned earlier how we've taken a new approach with this sensor to maximizing the field of view. And here you can see just a direct competitive comparison with a cell sample which we took recently. So this is the Sona with the full 4.2 megapixel, 32 millimeter diagonal. This is the closest competitive back-illuminated sCMOS using the same sensor type in the life science space, using a 25 millimeter version of this sensor cropped down. So basically, we're 62% larger field of view area with the same sample and same optical conditions. So that has a number of benefits. The field of view, from a fluorescence microscopy standpoint, it opens you to types of applications that simply can't benefit from seeing more of the sample. I mentioned one of them earlier. I mentioned two of them earlier. One of them was developmental biology, where you want to ideally image with high clarity a developing embryo. The other would be high content screening that I mentioned earlier, where you want to image very, very full fields of cells for their and examine their properties after exposure to potential drug candidates. So simply looking at more cells, greater fields of cells, gives you better information content, increases the throughputs of your measurements. But there's others looking at organoids is a good new area that needs a high field of view. You could be looking at tissue cultures where a higher field of view per scan would mean you'd have to do much less stitching of individual scans to get the full tissue imaged, and therefore increase the throughput again. And things like gene editing, where again you want to look at large fields of cells to select the cells whose genomes have been successfully edited. So yeah, that's, I'm sure, just the tip of the iceberg. There's lots and lots of applications which benefit from seeing more area. So how we utilize and how we access the field of view is a bit more of an intricate explanation. To me, the real value of this Sona 4.2 megapixel is in the flexibility of it. So yes, it's an 11 micron pixel, which on the surface of things actually feels a bit big for microscopy. But 11 microns is well suited to a 100 times magnification objective. And of course, you can use it in that mode. But actually, lots of researchers want to use it. They want to use times 60, times 40 lower mag objectives. Again, with the core objective of seeing a much larger on-sample field of view, but maintaining high clarity. So how do you do that with an 11 micron pixel? Well, you add a further step of magnification just before the camera. So this is quite a common thing to do in microscopy. For example, 1.5 times, 2 times additional magnification. So this is where it all knits together beautifully. In magnifying this image coming out of the microscope onto the sensor, if you have a small sensor, you're going to throw away lots of the image. But we've a big sensor. So that whole process ties together very nicely. That means we can utilize our much bigger 32 millimeter sensor with the output field of a microscope and capture it, because we've got a big sensor. And we can then use times 60, times 40, much more popular and attractive objectives to do so. So that's the benefit. How you actually achieve this magnification is quite easy to do. Some microscopes, a lot of microscopes in fact, have their inbuilt tube lenses, which provide an additional 1.5 or 2 times magnification. Lots of the microscope manufacturers actually have couplers which fit onto the exit ports of microscopes, which typically provide 1.5, 2 times, or 2.5 times additional magnification. Again, it's usually for this reason of adapting different pixel-sized cameras to the objective magnifications that people want to use. So it works really well with a large sensor, as it turns out. Now, if you can't access the necessary type of magnification just before the camera, inherently from the microscope, say, then Andor thought of this. We actually offer our own Andor magnifying coupler unit with a 2 times standard magnification, and that's compatible with many of the different makes and models of fluorescence microscopes, of modern fluorescence microscopes. So I'm close to the end. I just wanted to remind you again that launch of the Sona is next Tuesday, the 24th. At that point, you'll be able to go on and access some pretty decent tech notes that we've written, very informative tech notes, which give a lot more detail and explanation around the type of things which I've just written. So I mentioned the 7 reasons to consider the Sona as a back-illuminated sCMOS of choice for fluorescence microscopy. But there's also another tech note related to what I just talked about called optimizing field of view in microscopy. And again, it goes into much more detail and is much more instructive about how to achieve what I just talked about. So yeah, look out for that next week. Thank you very much for your attention. So between now and the launch, if anybody does have any additional questions, we've actually set up an email address, which we'll show at the very end of this presentation. We'll leave it on screen. So if you're desperate for more information, feel free to contact us through this email address. So thank you very much.
Okay, folks, I think we're out. So thank you very much for coming down here. I appreciate that. So online, we're just going to leave up a screen for folks that are online that has the email address. If you want to use your